everybody. Thanks so much for coming in at 7 o'clock. I know it's probably been a long day for most of you. Hopefully this is the end. I'll be around for a little bit after, so if I might end up a little bit early, you can feel free to kind of make the most of your time, or I will be here to answer any questions. But I won't be taking on questions on the stage, so I just wanted to set that expectation. So my name is Cecilia Dang. And I've been with AWS Lambda for about 5 years. I started as an engineer and transitioned into management a couple years back. I actually got my start in the games industry. I worked at Electronic Arts, working on the online gaming experience, which is what led me to AWS and web servers. I heard that there's bingo going on, so they might be kind of like, you know, having more fun than over here, but there's the casinos afterwards. Yeah, so I've worked on a lot of different problem spaces on Lambda. I've done talks on stream processing in previous years at reInvent. And right now, my team owns the asynchronous invocation and SQS Event Source side of things with Lambda. Is anybody in the room familiar with those two technologies or use? Cool, awesome, because that's what this talk will be mainly about. Asynchronous processing best practices is also going to include a few different ways that asynchronous traffic flows into Lambda. So I'll also be talking about a couple other avenues and best practices in general, a little bit of queue theory and just sort of what buffers are and why do we care about them and how it relates to our distributed systems, which is what all serverless architectures really are. So first, I'll be talking a little bit about what it means to be an asynchronous workload and what benefits and why you would want to have your workload be asynchronous. And then I'll talk a little bit about the different avenues of driving asynchronous traffic to Lambda. So this will include SQS Event Sources, stream event source such as Kinesis and DynamoDB, and asynchronous invocations. And at the end, I'll be diving specifically into the async invoke path, which is where a lot of the integrators, the existing integrators, go through to Lambda. So this includes S3 events, EventBridge, so CloudWatch events, and a lot of the existing services that drive real-time notifications to Lambda go through the asynchronous path. So I'll be talking about the responsibility and ownership on the Lambda side, and not as much about the generation of these real-time events on the integrator side. And then we'll be diving under the hood, what the asynchronous invocation stack kind of looks like on our end, how we address some of the concepts that I'll talk about earlier ourselves, yeah, and sort of just how that works. So let's talk about why async. So why would you want to have your workload be asynchronous? So one of the main sort of obvious reasons is as a caller, you're going to have immediate relief from latency. So I'm going to have analogies sprinkled out throughout my talk, and they might not always make a lot of sense, but that was the best I can come up with at the time. So in this example, say I want a cup of tea. But I don't want to have to wait around and make the tea and have the tea be ready because I want to go and do other important work. My realm of responsibility, I have a bunch of other stuff that I need to do and not wait around for this tea to be made. So at the end of the day, somebody is going to be responsible for making this tea. So I'm just saying, well, I can wait and hand off this request to have the tea be made. And because I'm saying that I have this allowance to wait and give this responsibility to somebody else, I can also say that whoever is responsible for making this tea or serving this asynchronous request can also be able to take on some of the resiliency involved with fulfilling that request. So for example, if the teacup broke while pouring the tea, I can have some expectation that the person responsible can take out another cup and pour that cup and fulfill that request. As far as the callee is concerned, or the caller is concerned, I made a request to get tea, and at some point it's going to get fulfilled. There might be some retries or error handling in your distributed system, as well as allowances for differences in how long it takes to service that request. So different teas might take longer or shorter amount of time to brew. So we'll talk a little more about why that is also very important to be able to absorb the differences in traffic, in duration of processing traffic, the next couple slides. So when you talk about why async, it's also very important to think about just why buffers in general, because a lot of these concepts stem from the awesome studies and conclusions that we've made with handling just networking in general. So there's been a lot of papers published and learnings that we've learned with just having the internet. So there's a lot of parallels with just networking concepts, and I'll kind of be drawing some of those parallels. But why buffers? So buffers really gives you that allowance to wait, and this is when I said I can have an asynchronous workload. That means that I can wait for things. And the importance of waiting we'll be talking about for the rest of the talk. By not having buffers, it means that you don't have this capacity to wait. And traditionally, what this meant in networking is that at some point, you're going to have variances in traffic and extra packets. And if there's no place to put these extra packets and have that wait concept, then you're going to have packets be dropped at some point. And what ends up happening is that you have an increasing rate of loss, and at the end, when you're receiving these requests, there's always going to be some kind of delay, a constant delay, and there's no way to make up for that. So similarly in a distributed system where you have multiple components, and each of these components have their own concept of an ingress and egress rate. So there's a certain allowance for how much traffic that one component can take. If you have a bunch of these interconnected, without buffers, you're going to have to be very careful with synchronizing traffic between the system. Otherwise, at some point, you're going to have that extra amount of traffic, and you don't have anywhere to put it, so it's just going to be lost. On the other, another dimension you can look at is if you want to have that resiliency and be able to do some error handling or retry, that's going to cause one delay that is going to be propagated throughout the system, and you're going to be even less resilient to more incoming traffic. So kind of just a way to sort of visualize it, I have this tightly interconnected series of components, and imagine that if they had gaps between the different components, and that's kind of the sending traffic between services. If you don't have that flow of traffic very tightly controlled, you're just going to have leakages if you don't have this capacity to wait around for work. So that leads me to this really great quote: "The road to hell is paved with good intentions." Okay, awesome. We need some buffers because I want to be resilient to some things like traffic changes, burst in traffic, or be resilient to some error handling. But on the other hand, what this gives you is the concept of backlogs. And you're going to have to understand and deal with this and deal with the complexity of backlogs, which is a different problem that you didn't have to face before. So that's that quote. So what are some of the trade-offs when you're thinking about asynchronous? We talked a little bit of how, the ability to wait. So generally, this ability to wait comes with waiting a little bit longer, because you do have to do that sort of transaction of handing off this request. And especially if you're going to be building in some resiliency, such as error handling, that might take some time too, and whoever's responsible for fulfilling that request. So that's just one important thing to think about when you're thinking about async workloads is, I have how much my service or my component can handle, how much incoming traffic and egress, and if I'm going to add some buffers, what is the extra latency that I want to be, what are the timeouts that I want to be thinking about when I have something that's making an asynchronous request. And the other really important thing to think about with asynchronous requests are backlogs. So if you have the concept of a buffer, you're going to have things ending up in that buffer. And when things end up in the buffer for a certain amount of time, that means that it's backlog. And this will happen with any sort of back pressure in your system. So anytime you're saying, hey, I can't take any more requests, and you're saying, okay, but I don't want to throw these requests away, I'm going to have it wait around somewhere, that's a backlog. So the real trade-off here that when you're talking about asynchronous is, do you want a backlog or not? Because the trade-off if you don't have a backlog is it's gone. But on the other hand, when you do have a backlog, you need to know how to handle it. What am I going to do with this backlog? And that's really what I'm going to be talking about for the next few slides is, all right, you're going to have backlogs at some point. What are the controls that you can use and leverage to deal with it, and how can you think about how to deal with your backlogs? So just to sort of back up a little bit, I'm going to talk about the different avenues of driving asynchronous traffic to Lambda, because then after that, I will be diving into the different controls that each of those options have. So async with AWS Lambda. First of all, you have the Lambda async invoke. So in that case, you just make a request. If you're familiar with the SDK, it's just an invoke, and the type is event, and that's it. It's kind of like fire and forget in today's world. And any concept of buffers, it's managed for you behind the scenes. So that's managed by my team, and that's what I'll be diving into kind of at the end of this talk. With Amazon SQS Event Sources, you manage the buffer. You're really bringing to the table your own queue, the SQS queue. And you have some controls already, like setting DLQ and setting the retry count, maximum receive count, and stuff like that, visibility timeouts. Same with stream event sources to Lambda. You're bringing the stream to the table. You're managing the Kinesis stream yourself. And you can kind of think of each shard within that stream as its own FIFO queue. It's a buffer where you have to process events in order. So when you grab a request at the head of the stream, you have to process it before any progress can be made on that shard. And what that kind of ends up bringing is the concept of a poison pill. Which means that if you have trouble processing that first batch of records, you can't actually make any more progress. So when we talk about that, it'll come up later, and we'll talk about how that can be addressed as well. So we talked about backlogs, and I want to kind of go over again what you want in a backlog, and what sort of what you want to keep a backlog. What's a good backlog? So you want it to be able to absorb traffic spikes. So that's sort of the intention of having these things. You want to be able to also absorb the amount of time that it takes to handle errors or retry on throttles and things like that. Another really important thing is to make sure that it doesn't last very long. So if you have a continuous backlog and it's not being drained or not being addressed, then it's kind of like defeats the purpose of having this type of thing. You also kind of want to, when you're thinking about dealing with a backlog, you might need to acknowledge fairness, because at some point you have a bunch of requests that you need to go through, and at that point in time, when you're dealing with that backlog, you might want to actually make sure that certain workloads are prioritized differently than other workloads. So imagine a line of people waiting for ice cream, and in this case, I guess at some point you cut off that line to ice cream, but in the real world, you never really stop incoming traffic. So the idea is that you don't really want to keep this steady state, having like a lot of people waiting. Because what it means is that any new incoming requests are going to always be waiting, and you're not going to be able to get to them in a shorter amount of time. So what do you do with these backlogs? Imagine the person being the one that's receiving these ice cream requests and trying to dole out ice cream. So some aspects or some strategies that she might provide is to prioritize different workloads. So for example, if there was some ice cream that expires a little bit early or is just not good anymore than other ice cream, maybe one thing to consider is to take in requests for those types of flavors separately from the other normal flavors. Or imagine that there's people in line and they want to request hot dogs or something that you just don't have, and it takes a long time to explain to those customers that you don't serve hot dogs and you only have ice cream. So in those cases, you might want to throw away those workloads, but maybe at a lower priority, because you actually want to be prioritizing the customers that want to give you money and have legit requests. So that kind of goes to prioritizing workloads. There's two sort of strategies that you can deal with it, which is delaying delaying the ones that you want to be lower priority, or just discarding them and you don't want to process them ever. The other side of things is you can simply increase the processing power. So that's just increasing the egress rate with which you're processing these backlogs. And so you can do that with just being faster. So the person can just be doling out ice cream way faster, or asking for help and having more people doling the ice cream out in parallel. So given that these are some of the strategies to deal with backlogs, I'm going to be talking about some of the controls to the paths to asynchronous that I talked in the previous slides. So let's first talk about SQS Event Sources, as this one kind of has some already natural concepts that allows you to prioritize workloads. With SQS, you can assign a DLQ by setting a policy of maximum receives. So that means that every time I pull a message off of an SQS, that message's receive count increases. And you can set a maximum number of receive counts before that message is discarded. And if you set a DLQ, then that message gets delivered to that DLQ. In this case, another SQS. So what this allows you to do is to ensure that incoming requests get serviced at an appropriate rate. And the requests that are having a little bit of trouble being processed, maybe there's some error that you want to be processing later, you can sideline those requests. And in this case, you can set another SQS event source to another Lambda that process it. But the idea here is that it's in complete isolation to your main queue, and it doesn't impact the main traffic flowing through it. So taking this kind of concept, we've added a bunch of new controls with stream event sources. These can be set through the existing event source APIs. So this is create event source mapping, get event source mapping. And using these APIs, you can set this concept of destination config, as well as maximum record age in seconds, maximum retry attempts, and bisect on function error. So let's dive into what these controls do. The destination config on failure is essentially like a DLQ. It allows you to choose, upon unsuccessful invocations and failures, delivering that record to that specific destination. And today we support SQS and SNS. What's important here is the two following features: maximum record age in seconds, which is essentially a TTL. So this is the amount of how old a record is going to be that you consider useful before you discard it. And anything before we discard, if you set that on failure for the destination, we will honor before anything is discarded. Similar with maximum retry attempts, you can set maximum retry between 0 and 2 attempts before that record is then either sent to your on failure destination or discarded. Bisect on function error is less of a traffic control. It's a way to help you with dealing with that poison pill situation that we talked about earlier. So just real quick, bisect allows you to, in parallel, process the batch that's been split. So if you continuously do that, you will eventually isolate the record that's giving you trouble, and you can deal with that record or that specific record individually without impacting any other messages that could possibly be in that batch. So given that we have these controls now, what you can do is when you have a stream, you can set max event age or max retry, and that's really specifying the priority or the value of the traffic to you in terms of how old or how many attempts that you've made for it. And then you can set the on failure destination, which will then serve as a sideline queue. And the destination for on failure, or destinations in general, and we'll talk about that a little bit later, the options are SNS, SQS, Lambda, and Event Bridge. In this case, imagine it's an SQS queue, and it can hold your lower priority workloads, and you can set a SQS event source to Lambda and have that be processed in complete isolation from your mainstream. Some examples of when you might want to do this. All of this is in relative to time, so we're talking about real-time processing and what real-time really means to you and your business case. So really thinking about the controls here, which is max event age. So how old do you think a workload is valuable to you, or how many retry attempts? So when do you think that you don't actually want to be stop or impacting your other traffic because this one is failing too much? For example, you could have things like Twitter stream, where you want to be having some maybe real-time aggregation or real-time analytics, and you don't really care if there's records coming in or messages coming in that's a little bit later or 5 hours later, but you do want to have a record of those ones in your sideline queue because you have some aggregate report that you want to do later. So you have these two tiers of what kind of workloads are important to you, and you want to process them at different rates. So very similarly, in async invoke, we've announced a bunch of cool new features that do to the similar things. These ones are a complete new set of APIs. It's a new configuration concept called the event invoke config. So this is a configuration specifically for your async invoke, or your event invoke. And you can set destination config as well as maximum event age in seconds and maximum retry attempts. So diving into these features a little bit more, what they allow you to do is for destination config, again, you can set an on failure, and this is very much like a DLQ. So granted, we do have an existing DLQ feature for async invokes. If you have both set, we will honor both, but the recommended path forward is to really use destination configs on failure, as that has a more cohesive place where you're setting all your future async invoke configurations. Maximum event age in seconds is a TTL, so time to live for your asynchronous invocations, which can be set between 60 seconds and 6 hours. And maximum retry attempts, you can set between 0 and 2 attempts. When you don't set these things, the default is 6 hours for event age and 2 attempts for retry attempts. That's what we do today. We retry 2 times. But what this allows you to do is, say I only really want the freshest invokes, and I don't even want to attempt retry any invokes. So setting that to 0 is what that allows you to do. So with these controls, you can have your asynchronous invocation and set the max event age and max retry attempts as rules of how important you want your async invocations to be and differentiate between that. And then you can also set the on failure destination to be SQS, SNS, Lambda, or Event Bridge. In this case, again, I have the good old SQS queue to be a sideline queue, and that can be processed in complete isolation from the rest of your asynchronous invokes using another AWS Lambda function. So kind of talking about the whole networking parallel things again. We talked about prioritizing or the different priorities of workloads. So there's this concept called buffer bloat in the world of networking, which is the existence of an excessively large or bloated buffer in the system that's just not being addressed and it's kind of being persistent. And what that impacts is the amount of goodput. So goodput is the amount of throughput that is stripped of all the retries and the overhead that might be causing all this buffer bloat. So at any given point in time, you might have a lot of throughput, but the amount of goodput, the amount of actual maybe fresh incoming traffic that's the part that's important to you, it can be quite low, and so that's something to be careful of. And my analogy here is, imagine you have a pile of vegetables, and at a certain point in time, you probably don't want to be consuming them anymore. They're just not it's just not what you want because they're rotten. So we talked about the priority of different workloads, and I had also mentioned just increasing egress rate. So this I call it just beefier processing, which is another way to address some backlogs. For these different avenues of asynchronous processing, on the back end, on the Lambda side, what we do is we scale in response to what kind of workload we're detecting. So for streams, like Kinesis streams or DynamoDB streams, it might be, one indication could be the pure number of shards. If you have a large number of shards, you're likely going to have a larger workload. For customer queues, it could be one of the signals is how many messages we receive every time we call a batch of records. So when we see that there is larger workloads, we increase the power of processing, essentially. And what does that really mean? It means that there's more parallel processing. So there's just more threads that's doing this work and asking for work and processing it. One thing to note, though, is for streams, and this kind of goes back to this in-ordered poison pill issue that I talked about earlier, you are limited per shard the amount of concurrent processing today. But there's a new feature announced called the Parallelization Factor that allows you to add additional parallel processing power per shard for a stream. And really the key here is you want in-order processing per partition key. And you could have multiple partition keys in a single shard. So say you set the parallelization factor to be 3 for your stream. That means that each shard could actually have up to 3 concurrency instead of 1. And how that works is, say we get a batch of records from that shard, and here I have workloads from the green and pink and yellow. And the resulting invocations can be 3 invocations, each with the batch of records for that partition key, and that's actually done concurrently. So doing this can allow you to have greater, beefier processing from your streams. And again, going back to some networking parallels, the concept of head-of-line blocking is a performance-limiting phenomenon where you have a queue of work to be done, and it's all being held up by that first packet. And one of the ways to address that is this concept of virtual output queuing, which is essentially, instead of having just a single queue, you have multiple ones maintained for the different types of workloads or different possible output locations. So we had talked about previously, having different buffers that can keep the different prioritized workloads, or even the parallelization factor for streams that allows you to do greater in parallel work. And the analogy here is, you have this person that's drawing out all these red bottle caps, but it would be a lot faster if at the same time you had people sorting out the blue and the green bottle caps, because they all have their own different requirements and they can be processed completely separately. And one thing to note for beefier processing, specifically for streams, and this is kind of just more controls in your processing than maybe controlling the traffic itself. But you can set a custom batch window. So this means waiting up to 300 seconds now to increase the size of one batch of records that goes to a Lambda invocation before it's invoked. So this was actually released a little bit earlier this year. So in this case, I get one batch of records, and before sending it for invocation, I'm going to wait around and get another big batch of records before I send it for invoke. A good talk, actually, that kind of dives more into the stream side of things is SVS406-R1, and that'll dive specifically into stream processing controls and talk a little bit more about the stream processing side of things. So. Now I'm going to talk specifically about asynchronous invocations and a little bit about how we do things under the hood to address backlogs and some of the stuff that comes along with it. So high level, we have this concept of a queue router. So that's something that takes in the incoming asynchronous invocation requests and routes them to our internal set of buffers and our internal set of queues. What ends up happening is that we can route multiple types of workloads or multiple workloads to a single queue. And so this is also a common issue with networking is for complete isolation, you would want to have a different buffer for every different type of workload. But in reality, this is highly unmaintainable and not practical in terms of costs and efficiency. So what ends up happening is that you have these workloads sharing the same queue, and that can lead to some interference. So in this case, you might have, I don't know how to work this. You might have yellow workload and the green workload take a little bit more time to be processed because it's actually waiting for the pink guy, which is not really desirable. So how we address this is with shuffle sharding. So who in the room is actually familiar with the concept of shuffle sharding? Okay, cool. So there's a lot of other talks that dives into the mathematics and probabilities of it. I'm going to be talking about how we've implemented it just in our specific use case. So in this case, when we have an incoming request and we want to route it to one of our queues, we consistently hash to a set of queues. So we say one of our shards, in this case it'll be 2. So we do the consistent hashing and we get back 2 queues. But which queue do I actually put my request into? In this case, we use this concept of best of n. So in this case, because there's 2 queues in our shard, I'm going to choose which of these 2 queues is best. And you have to define what best means with best of n. And in this case, best means the queue with the least amount of backlog. So I have the concept here of, say this white line, oh, you can't see that, sorry. Say that white line represents just, anything on the right side is the amount of traffic that I can actually keep up with, and anything to the left is some backlog that's going to induce a little bit more latency. So in the case that I have a yellow workload, and that's consistently hashed also to 2 random queues, and one of them actually overlaps with customer pink. In this case, the best of n strategy sees that there is some backlog in the second queue, and so I'm going to be routing the request for the yellow workload into the other queue that's actually quite empty and it's going to be able to service the request well. So this is a quick example of how we do shuffle sharding, but kind of taking a look over the overall space of things, we have a lot of different queues, and depending on the size of the shard and how many customers you have, the mathematical probability of one shard completely overlapping with another gets very, very minimal. And so that's the sort of key concept here. You're reducing the scope of impact that any backlog might possibly have in the system. Shuffle sharding is all about the scope of impact. And in this case, it's not a super rare thing to happen. Unlike other systems, you might be talking about fault tolerance for what you want to be like a particularly rare event. In this case, any customers at any given time could have a backlog. If you set your concurrency limit to be, say, 10, and then you hammer async invoke at 100 TPS, you're going to be having a bad time. So this might happen at any given period, and it might reduce the effectiveness of the shuffle sharding technique, which is why we also employ the concept of just sidelining backlogs. And this means that we are going to be detecting when a certain backlog is going to be pervasive and stick around for a while. And we want to make sure that that is isolated so that it doesn't impact any other workloads. So instead of having this pink workload be consistently hashed to queues that might be shared with other workloads, we're going to be routing it to its own queue. And in this case, this is a purple queue, not a purple workload, just to differentiate it from the blue queues. So sidelining guarantees this isolation. And I talked about, we don't want to give every workload their own queue. This hybrid approach kind of leverages the probability of shuffle sharding in the world where you're going to have brief moments of backlogs, while still relying on the determinism of isolating in certain cases. And the case is generally when we think that the backlog is going to be sustained or going to be particularly risky. So looking at the overall architecture a little bit more, when we talk about queue router, really it's a set of hosts. It's a set of hosts that's taking in incoming requests and then routing it to our set of back-end queues. And then when we talk about queue pollers, it's a whole fleet of queue pollers. There's a lot of them. And when they're processing the queues, they're processing from many queues at a time. It's actually an end-to-end relationship. And how does this relationship form? We have a set of control plane services, and I'll just kind of abstract that away as a queue manager. And so we have these services that are discovering work, and then you have the queue managers all asking for work. So at any given time, the queue puller itself knows how much work that it can take on, and so it'll ask for work if it can take on more work. And the queue manager knows if there's available work to be done, and then leases them to the queue puller. Doing it this way allows a bit of resiliency for when hosts are failing. So for example, if a queue puller dies, and the queues that it was processing are no longer processed by that host, you see that it's still being processed by other hosts. They're going to have to pick up a little bit of the slack, but the idea is that any given point in time, any queues or any work has some threads that are watching it and monitoring it and making sure that it's being processed. And when we have a host that comes back online and asks for work, it might not necessarily get all the same assignments or workloads. In this case, it has 2 of the original 3, and maybe that third one is processed by another host that is asking for work because it has the capacity to take on more work. At the end of the day, we also need the ability to scale for the heavier workloads. And I talked a bit about the whole beefier processing bit. So here we have still some remaining backlogs the pink workload has generated. And the queue pullers will react to that and increase the parallel processing to address those backlogs. Once those backlogs are done and it detects that, hey, everything's cool again, I'm not getting as many messages, it can also sort of back down. At the end of the day, the queue pullers are responsible for sending these asynchronous incoming requests for synchronous processing. So that's for the actual execution to happen. So diving into sort of more of the sending for execution side, we'll talk again about the controls that you have in how this delivery happens and how this final execution is done. So you can set maximum retry attempts, and originally this was 2. So if you set it for 2, what happens is you send for invocation, and if it fails, we're going to retry again. And that's retry number 1. If it fails, I'm going to retry twice. And so this meets the up to 2 times retry limit. If that fails, then that's a failure situation we're going to be discarding. And again, whenever we do this discard, it's a failure for processing this invocation, and so it'll meet the criteria for on-failure destinations. If you set a DLQ or on-failure destination, that will be honored before any discard happens. Same with the maximum event age. In this case, when we get a request and we see that it has exceeded the amount of time that it's useful to you, we don't attempt to send for invocation at that point. Instead, we go straight to the on-failure destination or we discard it. So again, this is because we want to get to the actual messages in the workload that is important. Setting the destination config is not only for on-failure. Any invocation result can be sent to a destination, including on success. So when you make that invocation, and whatever response you get back, whether it's a 400 or a 200, the request payload and context, as well as the response payload and context, will be sent to that destination. In this example, it's an event bridge. And so what this really allows you to do, besides having that sidelining ability and DLQ, is allow you to have that visibility into the on-success use cases. So destinations provide you that visibility, that where async invoke used to be fire and forget, it can now become fire and be notified. For example, when you make a call to get food, you don't have to constantly check, is it done or is it ready? Someone's going to be delivering the results of your request to you. Similarly with the destination on success, it lets you be notified in real time the results of your async invocation and execution, and allows you to, at that point in time, in real time, react to it and perhaps execute the next step in a pipeline of steps. We have a talk, actually SVS406, that dives specifically into Lambda Destinations, how it works, a demo, and some use cases. So this is a chalk talk, actually, and I believe there is a repeat tomorrow. Another great thing to think about when you're talking about visibility of asynchronous invocations is dwell times. So dwell time here I'm defining as the time between when that event was generated and when it's actually executed. So an example here is an Amazon S3 record, and you can see that there is the event time. So given that on this record you know when this event was generated and when it was sent for execution, in your actual Lambda code, what you can do is calculate the time between now, so when the function is actually being executed, and when that record was created. And then you can send it to CloudWatch as a metric. So here I've set the dimension to be just on the function name, but you can choose whatever. What this allows you to do is have some sort of history over all your invocations of what the dwell time is between them, and allows you to know if there's some issues going on in latency. Perhaps you're generating a bit of backlog because your egress rate is a lot smaller than your ingress rate. Totally aware that this is extra work that you do have to do, and having more implicit visibility for async invokes is definitely something that my team and we're talking about and improving the experience for. Another option is using AWS Xray, and that allows you to trace one particular invocation. So for that one particular invocation, you can see what the results were, so in this case, and also how long it took. So in this case, the function is called DynamoDB execution function, and the dwell time is the time between when that record was made and when it was actually sent for execution. And in this case, it succeeded on the first attempt, but if instead the result was a 400 and you had set, you would see subsequent attempts, and it would look like attempt number 2 in another line and attempt number 3. So this is a really great way to have sort of dive into one specific example and kind of have a sample of what's going on in your system. So yeah, that's kind of like an overview of asynchronous invocations in general. I did want to talk about some of the other talks that dives into some of the concepts that I had talked about. So SVS406, that's specifically around Lambda Destinations. Some people on my team is doing that talk and going into doing a demo and talking about the specific controls for destinations, as well as some example use cases. SVS417 is on stream processing and the new controls that we had released for stream processings in particular, and talking about some use cases there. API 304 is on SQS Event Sources. So another great thing that we had launched was FIFO queue, so kind of dives into that one. And then 405 and 407 talks about, in general, best practices and resiliency when you're building a distributed system. So a little bit more on queuing theory and shuffle sharding and the mathematics behind it. So again, this will end a little bit early, but I will be here and to answer any of your questions. If you want to learn more, there's a bunch of great resources. And don't forget to fill out the survey on the mobile app. Yeah, thanks for coming and joining.